Uh, Good evening, dear student, and welcome to this other edition of our functional analysis class. In this presentation, we are going to look at a few examples of the application of the Lebesgue theory. As I indicated during the last presentation, today's series of examples will tackle first of all on sigma algebra. We are going to look at sigma algebra generated by a collection of subset of a given non-empty set. So the problem goes as follows. So we are given a non-empty set omega. So let omega be an non-empty set. And we consider A to be an element of the power set of omega. So in other words, this means that A is a subset of omega. So the problem statement consists of determining the sigma algebra generated by calligraphic C, which is the collection consisting of the single subset of omega A. So in other words, we want to find sigma calligraphic C. So that's what we want to determine. So by definition, what is a sigma algebra? So by definition, we know that a sigma algebra generated by C is the intersection of all the sigma algebra F, X, sigma algebra containing C. So in order to construct this sigma algebra, first of all, we know that C is contained in the sigma algebra generated by C. So in other words, we have already some elements of sigma C. So those elements are, first of all, A is already an element. So A is an element of the sigma algebra generated by C. And also we know that the empty set and omega itself are both in the sigma algebra generated by C, right? Now, the definition of the sigma algebra, because it's an algebra, all the complements, so the sigma algebra is stable by complement, right? Stable by complement. So this implies that the complement of A, the complement of the empty set, which is omega, and the complement of omega, which is the empty set, are also in the sigma algebra generated by C. So from all this, we can say that the set made of the empty set, omega, A, and A complement, this set is contained in the sigma algebra generated by C. Now, if we can prove that this set, which we denote by calligraphic F, if it is a sigma algebra, therefore, it will contain the sigma algebra generated by C. Why? Because it contains this contains already C. So this contains C. Why? Because all the element of C, particularly A is already here. So C is contained there. So if you can prove that F is a sigma algebra, it will contain the sigma algebra generated by C, and therefore the equality will hold. So from the above, what I just said is that F is contained in the sigma algebra generated by C. So this comes from this result. Right? So from this, we have this result. Okay, so let's prove that. That F is a sigma algebra. So the first axiom of a sigma algebra is satisfied. So the first axiom is that the empty set, which we can see listed here, is an element of calligraphic F. Right. Now, the second axiom let we denote that B. Let B be an element of the sigma algebra. So B can be any of these elements. So If B is equal to the empty set, B complement is omega, and this is an element of F. Now, if B is equal to omega, B complement will be the empty set, which is an element of F. If B is equal to A, B complement, which is A complement, is in F. And finally, if B is equal to A complement, B complement, which is the complement of A complement, which is A, is still in F. So F is stable by complement, right? So with this, for any arbitrary element F, for any arbitrary element B of F, its complement is always in F. So the last axiom, so if you take a sequence En, a sequence of element of F now we set A, oh no, not A, but let's call that B. The countable union of all these elements Bn. Right? We want to show that this countable union is still in F. Okay. Since we have a countable union, in our case, actually, our countable union will be a countable finite. So because since F has finite, F is a finite set, right? F is a finite set. So there are terms of this sequence that will repeat because a sequence has infinitely many terms. So this sequence will be stationary at a certain point, or there are there are set that there will be duplicate. Actually, that's what I want to say. There will be duplicate. So due to the fact that F is finite, if you take such a sequence, either there are terms that will repeat, or all the terms will be stationary. So there are many options, right? There are many ways we can construct such a sequence, right? So first of all, we can take distinct. So let's take so we can construct the sequence right? Because it's an arbitrary sequence, so I can construct it because it's we can construct our sequence B Bn such that B1, of course, we can do this without loss of generality, such that B1 is the empty set, B2 is omega, B3 is A, B4 is A complement, right? And for n greater than or equal to 5, we can set B n to be, let's say A, for instance. You can take all the term equal to A, or Bn equal to A complement, or Bn equal to omega. Or still Bn equal to the empty set. So this is a possibility, right? So we can consider this particular case. You can consider this particular case. So you can see that this union so in this case, B, which will be the union, countable union of Bn for n in n, meaning that it runs from 1 to infinity. So what would be this union? Actually, we are taking the union of all the elements of A, sorry, of F. So this is F. So if we take the union of all these elements, it will give us omega, right? It will give us omega because A union A complement is omega. Omega union omega is omega. Omega union the empty set is omega. So as long as in our sequence we have A and A complement, the union will always give us omega because that will be the largest union that we can get. So as long as that sequence contains omega and omega complement, so this will be equal to omega, and this is in F, right? So we can say here that as long as the sequence contains omega and omega, A and A complement B, which is the union of the Bn, will always give us omega. Right. Okay. So if it does not contain A complement or A, if it's just stationary, equal, let's say, to the empty set, the union will be the empty set, which is still an element. If it's stationary, equal to A is still in F. So we can construct, we can take many combinations, right, of these various elements. We will still end up with the fact that B will be an element of calligraphic F. So with this one, we can conclude, this is just an illustration, and we can use a more elaborate approach to do the same proof. So we can conclude here that F is a sigma algebra. Okay, so F being a sigma algebra, right? What is the conclusion of this? F being a sigma algebra containing F, it will contain the smallest sigma algebra containing F. So F sigma algebra containing C, this implied by the definition of sigma that sigma C is containing F. Why? Because sigma C is the smallest sigma algebra that contains C. This is a sigma algebra, it contains C. And sigma C is the smallest sigma algebra that contains C. So it will be contained in any sigma algebra that contains C. Or still, what we can say, that's actually by definition. So let's go back to the definition that I wrote here, this one. So this is the intersection of sigma algebra containing C. So this will be contained in each of these F. So sigma F is contained in F. So we have already seen from star, if I can call this star, that F is contained in the sigma algebra generated by C, and this last result give us the inclusion in the other direction. So if we group star and double star, we conclude that, in conclusion, we conclude that the sigma algebra generated by C is F, which, from what follows above, is the set made of the empty set omega A complement. So this is the sigma algebra generated by A. By the singleton A. Okay, so the next example example 2. So this, okay, this example 1, the next example, let's call that example 2. So let E So let E be a subset of a non-empty set X. So we take a subset E of a non-empty set X. And we assume that E is countable. So we define S to be the set of element of the form right? So actually, this S is a collection of sets. It is a subset of the power set of E. Okay, so that's what we have. So this is a collection of subset of E. Why? Because if I take an element here, if I take, let's say, A, an element of S, it implies that we can find an element of E such that S is oh no, sorry, such that uh, okay, that's not okay. This is the simplest case, but it can be more, right? So we can say that we can find okay, this is just a particular case, right? It's just a particular case. Actually, what we can write, this is S is actually the union of such set, right? This S is the union of such set. But it doesn't mean that it's just a singleton, right? So if A is a singleton, it will be made of just one element. So it can be made of one element, it can be made of a finite number of elements, or it can be made of infinitely many elements because this E is countable. It is countable. Right? So it can be any of these. It can be any of this. But in any way, what I want to show here is that the element that we will get here will be element of this form. So A can be finite, that is x1, maybe up to xn, where all these xi are element of E. So all these elements are also in E. So A will be a subset of E. So A is contained in E. If it's contained in E, it means that it is an element of the power set, the power set of E. So it can be finite, it can be infinitely many. So we can, A can also be a certain x1, x2, right, up to infinity, because it's countable. All right, so this is just to show the structure of A, right, with this definition. This just gives us an example, some example of what an element of S can be, due to the fact that E is countable. Okay, so now we are going to discuss if we have a subset of this E, let's say X for A, for instance. If we take A to be a subset of E, and since E is countable, so these two information will imply that A is an element of the sigma algebra I've not defined the problem statement, so let me quickly do that. So what is the purpose? What are we trying to do here? Let me state the problem, right? Let me state the problem. What are we pursuing? So this is the problem statement. So what we are asked to do is to determine the sigma algebra generated by S. So in other words, we want to find sigma S. So this is what we are trying to determine. Okay, so if we take A subset of E countable, I was saying that this A will be an element of the sigma algebra of S. Why? Because A, in fact, A can be written, because it's a subset of E, and E is countable. So we can write A as a countable union of X of this form where X is in E. So we say that the union is countable because E is countable, right? N is countable. So each time we take a union, when we have a sequence like this, N, here. Now, if you take the union of all these, because N is in N being countable, this gives us a countable union. So this is a countable union because N is countable. Now, if E is countable, and I take the union on element of a countable set, that union is a countable union, right? A is a subset of E. So each element of A is in E. Obviously, this union is not, otherwise this might be E, but it's not, right? We take all the union of X in E, but actually these X are the X that are in A. But we indicate that those X, because they are in A, they are also in E, right? So because of the fact that this is a countable union, but we know that each set of this form is in S, right? An element of X, an element of S is something of this form where S is in E. So each of these points is in S. So what does that mean? It means so since this singleton X is in S, S is contained, right, in the sigma algebra generated by S, right? So in other words, this singleton X is in the sigma algebra generated by S, but because it's a sigma algebra, it will contain, actually it's stable by countable union, right? This being a sigma algebra, it will imply, so these two informations, this information and the fact that it's a sigma algebra, this will imply that the countable union of such element is in the sigma algebra. That's the definition of sigma algebra. Stability by countable union. X in A. In E. This is exactly A. So A is in the sigma algebra. So that's exactly what we have here. So the next step if A is a subset of X and the complement of A is a subset of E. So what do we need to distinguish this case? Because remember that here, E is a subset of X. We consider A to be a subset of E. So it can be a subset of E if it's a subset of E, it's also in X. But we can have the case whereby it is in X and its complement is in E. And we are going to use this first proof, this first condition. If A is contained in E, we are going to use that in this case, right? So this is the situation. So we have X like this. Let's say X is the largest set. This is X, and we have a subset inside here, and this subset is E, like that. So in the first case, we took A inside. We took A inside here. In E. But now the second case, we are taking A inside X and its complement is inside E. So that's the second situation. Good. Now, if A complement is in E, we can repeat what we did here. If A complement is in E, it means that that same A complement is in the sigma algebra generated by S. That's exactly what we did here. Why? Because this E is countable, right? So E countable. So this implies, similar to what we did here in the first. So this will show that A complement is also in the sigma algebra, right? But because this is a sigma algebra, it will also imply that A, which is the complement of an element that is stability by complement, is also in the sigma algebra generated by S. So that's stability by complement. So what have you just shown? So we have the partial result. If we define F to be the following set, a set of subset of X such that, so let's look at the first property we found here. A can be a subset of E, or A complement can be a subset of E. Right. So we define F to be the set of A, subset of X, such that either A is in E or the complement is in E. So this is contained in the sigma algebra generated by S. So such an A, we saw that such an A subset of E is in A is in the sigma algebra generated by S. And if we take the complement of A in E here, if the complement of A is in E, that same A is here in the sigma algebra. So in conclusion, we have this result. Now, if this F, if we succeed to prove that this F is a sigma algebra, we'll conclude that the sigma algebra generated by S is F, right? So if F is a sigma algebra, then what we are looking for, the sigma algebra generated by S, will be equal to F. Why? Because this F contains S. If it is a sigma algebra, it will contain the smallest algebra containing S. And we have the inclusion in the other direction. So if F is contained in sigma S and sigma S contained in F, there will be equality. So let's prove this one, what I've just written here, before proving that it's a sigma algebra. Actually, this one, I'll ask you to do this as a homework. That is to show that F is a sigma algebra. So that's the homework. Show this. So the homework is this one. Show that F is a sigma algebra. So now let's show this one, that S is contained in F. S is contained in F if We take an element of S, A will be a subset of E. I think I proved something like that before, right? I don't know. Wait, let's see if I did the. Yes, I think I did it. When in the beginning, when I stated this problem, this example, I said that this S is a subset of the power set, meaning that any element of S is a subset of E. That's exactly what I did. I did it already. Okay, but let me repeat it again. So any element here, if I take an element of S, it is a subset of E. That's exactly what I did already, but let me repeat it again. Let me repeat it again. If A is in S, A will be contained in something of this form. Because E is countable, it will be something of this form. X1, X2, X3, Xk or Xn, up to infinity. So it's something of that form. It will be contained. So meaning that A will be written as the union of element of this form. So we can see that each element here is a subset of E. Okay, so if it is a subset of E, what is the implication of this? The fact that it's a subset of E, this will imply that A is in F. And this is by definition of F. a definition of F. So let's look at the definition of F. F is defined to be subset of X such that either that subset of X is contained in E or its complement is contained in E. But we have this already. The fact that A is a subset of E is enough to say that A is in F. So we have this. So we have just taken an element of S here. We show that that element of S is also an element of F. So this ends the proof. So the homework now is to show that this F is a sigma algebra, that's all. And that shouldn't be difficult. So the last example that we are going to tackle is the following, and that will be the last one for today. And we'll continue maybe tomorrow. So example 3. Let the pair X calligraphic F be a measurable space. Measurable space. And F, F a mapping from X into Rn measurable, and finally G defined from Rn into R a Borel simple function. So we are asked to show that G, so the composition of G with F is a simple function. So this is the problem. Okay, so we are going to write the fact that this function g is measurable. I mean, it's a very simple function. What does that mean? So g, Borel's simple function, implies that we can find aj, an element of R, and a set, a Borel measurable set A, J, in the Borel sigma algebra of Rn, and this is true for J, taking the value 1, 2, up to a certain k. That is a finite number, right? So we can find a finite number of real number aj and the corresponding set capital A sub j in the Borel sigma algebra of Rn such that the function j can be written as a linear combination of aj, indicator function, capital A sub j, where j runs from 1 to k, for instance. So this is the definition of a simple function. So from this implies, this will imply that if we take the composition of the G with F, G composition F will be equal to the sum J running from 1 to K AJ, indicator function of A sub J, composition with F. So we compose with F to the right? So we apply F, composition F on both sides of this equality, we get this result. But what is this? What is this? How do we define this composition? If we take the indicator function with another function, what is that? So this gives us the sum j running from 1 to k a j indicator function of the pre-image of aj. Now, for this to make sense, we need the function or the set, because this is the indicator function of this pre-image of aj. So if the preimage of AJ is in the Borel sigma algebra of Rn, we are done. This will give us a definition of a measurable function. I mean, of a simple function. Because in the definition of a simple function, the indicator function, or the set of which the indicator function is of, it should be measurable. Right. Now, in this case, is it measurable? Yes, it's measurable because f is measurable, right? Because that's the hypothesis we have here. And the definition of a measurable function gives us a result. So in the hypothesis here, we say that f is measurable. So it is measurable. What does that mean? It means because Rn here is endowed with the Borel sigma algebra on Rn. So if I take an element of the Borel algebra of Rn, its preimage should be in F, because it should be here in the sigma algebra on X, which is F. Not the Borel sigma algebra of Rn, but the Borel sigma algebra of F, right? I think I made a mistake there. Okay, so we conclude. Since f from this x to Rn is measurable, and AJ is Borel measurable. This implies that the preimage of AJ will be in the sigma algebra over X, which is F. And this is true for any G. So this completes the proof. So from this equation, let's call this maybe triple star. I think we had a double star before. We had a double star somewhere here. Oh, yeah, we had a double star there above. Or I can just call it equation 1 to avoid any confusion. You can just call this 1 because it's a different problem. So I could call it 1, 1. To say that is the first equation of, no, this example is example 3, né? Yeah, 3, 1. So we call this equation 3, 1. So from 3, 1, we conclude that G composition F is a simple function. And this ends the proof. So before we part, let me give you a series of homeworks that you should do. Homework. So the first homework, I will call it okay, let's call this problem 1. So in the following, we let the following. So in the following, we let K and K prime. Okay, so because the element of the, I mean, this is a family, so we take calligraphic. So this will be calligraphic K and calligraphic K prime. We take these two to be a collection of subset of X, where X is a non-empty set. Definitely, X is a non-empty set. So the first question here is to show that if E is a, that's calligraphic E, is a sigma algebra, then sigma algebra generated by E is equal to E. Second question, find sigma K that is sigma algebra generated by K for K be the singleton made of the empty set, and K the singleton made of X itself. The last question, question 3, show that if K is contained in K prime, which in turn is contained in the sigma algebra generated by K, then the sigma algebra generated by K prime is equal to the sigma algebra generated by K. So this is the first problem. The second problem is so problem 2. Let calligraphic E be a sigma algebra. In X. And X0 a subset of X. First question, show that calligraphic E sub 0, which is defined as the set of elements of the form A intersection X0. Of course, such that A is an element of calligraphic E. So this set is a sigma algebra. This time is a sigma algebra in X0. The second and the last question, show that if calligraphic E is a sigma algebra generated by K, then calligraphic E sub 0 will be equal to the sigma algebra generated by K0. Where K0 is defined to be the set of the intersection of A and X0 such that A is in K. And to do this one, there's a hint that will help you to do this. So the hint so the first one this follows from this first question from 1. They follow from that first question. Now, to prove the converse, show that this set is a sigma algebra. Sigma algebra in X containing T. So I hope with this one you or, you have a good immersion into Lebesgue theory. Thank you so much for your kind attention. God bless you and see you next time. Bye-bye.